Okay. Hello, everybody. I think that more people will be joining soon, but there is around 20 of us as of this moment. And I think it's safe to start because we are on a tight time frame. So I will start immediately by sharing my screen, as we have added all of the slides from our speakers into one document. Just let me know if you can see my screen.
Yes.
Okay, great. Thank you so much. Usually there's no problem with this, but it's always safe to ask. Okay, so thank you all for joining. My name is Julia Mitrovic. I am part of the STELAR project, and I am from Foodscale Hub, who is partner on the STELAR project. You are here today on STELAR's and TITAN's joint webinar on semantic strategies for improved agri-food data management. And I will just give a quick note, a quick overview of our agenda, and then go over some house rules. First of all, thank you for joining. We have been planning this webinar for quite some time, and it's great to see it happening finally. We will be first speaking to Catherine Roussey, who is from INRAE, and who will be telling us what are knowledge graphs and why are they important. Then we will give the word over to Dimitris Skoutas and Petros Skoufis from Athena Research Center, and also to George Marinos from Agroknow. And they will be telling us more about constructing a knowledge graph from unstructured food safety incident reports. This will actually be insight into the STELAR project. Next, we will be speaking with Bernadette Durand from INRAE, and also Chanmeet Kaur from the Open Food Chain. They will be introducing us to the TITAN use case and the network of semantic resources for the food supply chain. Finally, Theodor-Christian Chirvasuta will lead us into the subject of data pipes, of extended data pipelines for a circular economy. And we have planned a short Q&A session at the end of the webinar. So please, you are encouraged to leave your questions in the chat box. Now, before we start, and before I give the floor to Catherine, a few house rules. When it comes to this webinar, you have seen that it is being recorded. We will ask you all, when you are not speaking, kindly mute your microphones. This is just to avoid some distractions and some background noises. And also, kindly please close your cameras. Although we will be asking you at the beginning of at the end of the webinar to turn your cameras on for a quick photo. And like we have said, we will have a Q&A session. So you are invited to actively participate by leaving your questions in the chat box. Okay, great. I have just looked at the chat box as I have seen already some questions, but all is well. Catherine, I think that it is safe that we move on with your slides. Let me know with the word next when you want me to change the slide. And yes, just one more thing. Sorry, before we begin. We are on a very tight time frame here. We have 7 speakers, an hour and a half. So I will be maybe unmuting myself at some moments to let our speakers know how much time they have left. Okay. So Catherine, please, you can start.
Thank you very much. Next, I will introduce you semantic web technology and knowledge graph. Next. So no, the second slide. Could you go? No, here. Okay.
Okay.
So
here.
First, I would like to propose some definition, because there is no consensual definition about what is data, information, and knowledge, and I want to be sure that we speak about the same thing. So for me, data are pieces of information that can be recorded, processed, analyzed, and communicated, whatever their natures. And raw data are data not yet being processed or contextualized. So data are perceived by humans and processed by machine. Information are data plus meaning, and only humans could understand the data. But to do so, they need context. And for computer science, it means that the data should be typed, and the type should belong to the data schema. And we speak about knowledge in computer science when information are formalized in a specific language called knowledge representation language, and the type of processing that this type of language could do is logical inference. It means that you could create new knowledge from existing knowledge. For example, when you have the relationship is composed of, and you know that the relationship is the transitive ones, you have a grapevine which is composed of bunches. Bunches is composed of grape. So because the relationship is transitive, you could deduce that grapevine is composed of grapes. Next. So I would like to introduce the word ontology and when it's come from. In the 70s, expert system was a branch of artificial intelligence, and their goal was to mimic human decision procedures. In the 90s, those systems have evolved and become now knowledge-based systems, where domain knowledge are separated from problem-solving knowledge. And this is the time where ontology appears. Ontology are a formalization of stable and consensual domain knowledge. The problem comes with the main definition of Gruber, which is the most well-known, and it says that an ontology is an explicit specification of a conceptualization. The thing is that any computer scientist which is sketching a UML diagram is doing a specification of a conceptualization, but it's not an ontology. Ontology, the main important part, it should be a shared conceptualization. It means that there is a community of users who commit to this conceptualization. So we would like to speak about a specific part of ontology, which is web ontology. That is data schema formalized is one of the language of semantic web technologies. Next. So all these languages are based on the graph syntax. Composed of a triplet. A triplet is two nodes, subject and object linked by an arc, an oriented arc. All these elements have a web identifier called URI, and some of the node subject of object could also be blank node. It means that you don't need to know the identifiers. And for the object node, it could be also literal. That means a string of our integer. You have an example of the data schema uses the graph syntax in order to describe two classes, person and company, and an object property, which is a predicate that link two instances of two classes working. And the person class is specialized with two subclasses, sportsman and soccer player. The company class is specialized with another subclass with a soccer player. Next. He's missing, there is another one. Yeah, this one, thanks. And based on this data schema, you could describe the information about Messi soccer player, which play in the Barcelona team. Next. So RDF is the syntax, and based on this syntax, you have different languages to describe data schema. RDF schema, which is a plain schema, ontology web language, where your schema contains more constraints. Skoufis, simple knowledge organization system, which is used to store thesaurus or terminology. And schema.org is a set of data schema built collectively by different partners. All these elements have a web URI, and you have different type of format, JSON, XML, or Turtle ones, which is more a text format. And I will speak only about the language for schema. Next. So for the standard web, World Wide Web Consortium organization, an ontology formalized vocabulary of terms that cover a specific domain and shared by a community of users. They specify the definition of term by describing the relationship which is with other terms. There is several use for an ontology. First, it should normalize a term. That means you have to define an identifier, which is a web identifier. The identifier should be associated with a label, and you have to provide a meaning with a natural language definition. The normalized term could be defined using the Skoufis model. When you have your terminology, now you have to select which term will be used to represent an element of the data schema. Some of those terms will become class, others will become relationship, which is called also object property. Other term will become attribute, which is named data type property. And your data schema can be used to integrate multi-source data with RDF schema language, for example. If your needs is more oriented about knowledge management, that means you have very specific, very good information sources that you want to share on the web. You will use your data schema as a metadata schema in order to retrieve your information source, or you could have another type of schema which is more constrained in order to produce logic inferences. And that you will use to do that ontology web language. And when your data set are organized with this ontology and published on the web, you call it a knowledge graph, which is a set of facts. Next. So you have to publish your data set, your knowledge graph on the web, and provide an INRAE and put it on the web is not enough. You have to link your knowledge graph to others. And you have an example of what is called a local open data cloud, where all the nodes represent a knowledge graph. And you can see that there is a different link between the knowledge graph. It means there is different type of links. You could reuse an ontology to organize your knowledge graph, or you could specialize an ontology, or you could reuse another part of the knowledge graph. Or you could say that in your knowledge graph, you have a representation of a physical object, and there is another graph with we represent the same physical object, and so you would say that your representation are exact match with the representation of the other knowledge graph. There is different kind of link, and you have to be linked to the others to belong to the linked open data cloud. Next. And when you do it correctly, it means that you have provided fair data, findable, accessible, interoperable, and reusable. Next. So using ontology is not so easy. You have to understand their design pattern. Design patterns are very small, reusable modeling that resolve recurrent ontology development problem. And it's also good practice modeling. You could find this design pattern in foundational ontology, like basic formal ontology or Dolce, or you could find them in core domain ontology provided by the W3C, like the semantic sector network ontology or the time ontology. ODP are also published in dedicated conference. Next. So this is an example of the design pattern of the semantic sensor network ontology provided by the W3C. There is 10 classes, and you have to understand how this class has to be used. The central class is the observation class, which is the activity of measurements. You observe a natural phenomena, any phenomenon which is named feature of interest. You measure the characteristic of this phenomenon, which is the observable property. The sensors is the device of the person who do the measurements, and the measurements, the activity of measurements as a result. You can notice that in the SSN ontology, there is no information about the unit of the measurements. It means that you have to find another ontology to describe the unit. Next. No. Previous one. There is another one before this one. Go back. No. No. 17, 16. Yeah. Okay. the black box should highlight the very important classes where are the design pattern. So, sorry, can you go to the 17 slide? Next.
So this is the next one, yes?
Okay, this one. It's another ontology from the W3C, which is called probe. Oh, I cannot see anymore the slide. I have no more slide on my screen.
Apologies, something happened, some kind of a bug. So let me just see if I can fix this. I had a notification say that somebody else also tried to share and that multiple sharing is not allowed. Let me just see what happened.
I could finish. It was nearly the end of my talk. So in this,
of course, continue. Then we will check the slides.
So at the end, in this very simple ontology with free class, the design pattern of the probe ontology implies that you use the free class, and the activity class is in most part of the time the class that nobody is using. So to conclude, ontology are fair data schema, but they are not so easy to reuse because you have to understand clearly their design pattern. So you have to read correctly the definition and the documentation of the ontologies. Moreover, semantic web technology are changing the modeling paradigm because you have in a graph-based, not in the frame-based. Property are first-class citizens, means that they are as important as classes and they do not belong to the class. And using ontology, you are in the distributed world. So you are in the open world assumption. It means compared to the database, in the database, what is in the database exists and what it is not in the database does not exist. In the distributed world, you have to know what is true, what is false, and what you don't know. And this is the end of my talk. Sorry for the...
Okay, thank you so much. I will just change one setting as we had a slight bug. I will unmute, I will mute myself for a few. Hello, everybody. I think that you can see my slides once more. Sorry about the delay. Catherine, thank you very much. I will give then the floor to Dimitris, Petros, and George to present STELAR and our use cases. Dimitris, can we start with your part?
Yes. Hello and welcome, and thank you for participating in this webinar. My name is Dimitris Skoutas. I'm a researcher at Athena Research Center and also the coordinator of the STELAR project. In this session, we will be presenting some part of our work that we are doing in the STELAR project, particularly focusing on knowledge graphs and applications in the agri-food domain. I will start with a very brief introduction to the project itself, so that you have an idea about what the project is about. And then I will give the floor to my colleagues, first George Marinos from Agroknow, who will describe in more detail the relevant use case and the motivation, also with some technical information. And then Petros Skoufis, also from Athena Research Center, who will provide more information and details about the work we have been doing about LLMs and knowledge graphs. So next, please. Just a few words about STELAR. The full title of the project is Spatiotemporal Linked Data Tools for the Agri-Food Data Space. It is a project funded under the call for technologies for data management. The duration is 3 years, and currently we have just entered the third year of the project. And there are several partners, as you can see here, 9 partners in total, both from academia and the industry. Next, please. Regarding the challenges, the main focus of STELAR is on data pipelines for AI applications. The observation is that there is typically a large gap between raw data that someone finds in some sources and the type and format of data that one needs as input to ML and AI applications in order to have reliable results. This involves different steps, starting typically from data discovery, finding out which data to use, which data are appropriate for the task at hand, how to rank or compare different data sets and data sources. Then moving on to data integration, because often a single data source does not contain all the information, all the features that are needed for an analysis. And then several challenges arise due to the fact that there are different entity identifiers, there are different spatial or temporal resolutions in different sources, and so on. And then moving closer to the ML input, again, there are challenges related to data quality, for example, erroneous or outlying values, missing values that need to be imputed, or the fact that one needs typically labeled data to some extent at least in order to train or fine-tune the models. These are the types of challenges that we're trying to address in STELAR. Next slide, please. And to this end, our vision is to develop a so-called knowledge lake management system to turn raw data lakes into knowledge lakes. And this involves 2 main pillars. On the one hand, the KLMS platform, which provides several core components, among which a knowledge graph that semantically annotates and enriches information about datasets and workflows. And on the other hand, the KLMS toolkit, a set of tools that address different stages in the pipeline, as mentioned before, relating to data discovery, interlinking, and annotation. We have several pilots in the agri-food domain covering different stages of the food supply chain. We start with food safety, which will be the focus now in the next part of the presentation, where we analyze food safety data to extract valuable information, but we also have other use cases relating to crop yield prediction and precision farming, like developing suitability maps and so on. And with this, I will give the floor to George Marinos to describe the use case relating to food safety and knowledge graphs in this context.
All right, excellent. Thank you, Dimitris. I'm George Marinos. I'm a machine learning research engineer in the innovation department of Agroknow, and I'm going to present the core objective of Agroknow pilot and things that we also working within the STELAR project. So starting from the Agroknow's objective, let's assume that we have a web spider that is searching new web sources that publish official announcements for food records, because Agroknow's main component is to find and collect official food incident announcements worldwide. And therefore, once we find those web sources, we used web crawlers in order to crawl those new announcements from the well-known so far official authorities and websites, and we end up having some specific web pages where the objective is to identify the entities from each web page with regards to food safety recall announcement. And finally, once we extract those entities, to store them in a structured way in the databases. So next slide, please. All right, so we're talking about entity recognition, which is useful for 2 types of food safety related data in Agroknow pilot. we're talking about food incidents, which are described mainly in the right-hand side of this picture. And we're also talking about regulatory data, which are regulations, where the entities are, for example, the specific food ingredient, the specific hazard, the total amount above which the specific concentration is considered harmful for people, and so on and so forth. And through this task, we aim to identify those entities from the texts and store them in a structured way in our databases. The same is for food incident announcements, but this time is for food ingredient, for the time that the food incident happened, the region, the hazard of the food ingredient, and so on and so forth. Next slide, please. All right. Here we have an example of a food incident announcement from FDA. FDA is a well-known web source which officially announces food recalls. And here we have an example of what we feed our algorithms, the raw text, for example, and what we aim to identify. For example, here we would aim to identify entities like the date, which is, for example, July 29, the specific hazard, which is linked to Chronobacter sakazaki, the specific ingredient, and we end up having a conceptual knowledge graph where in the right-hand side of the picture, we see that FDA is linked with a specific link of the web page. We have the brand name, which is Lyons. We have a slightly different company name, which is Lyons Magnus. We have the hazard, which is microbial contamination. We have the date, and this constructs, in a dummy example, of course, our knowledge graph. And this expands to all the data that we aim to feed in our algorithms. Next slide, please. So in our task, I will present some details regarding our approach, and this concerns the regulatory data. We have employed some traditional transition-based models and some pre-trained large language models, since we are in the era of LLMs. For the first category, transition-based models incrementally build structured outputs using a sequence of actions or transitions. And they are used commonly in applications like dependency parsing, but also in name entity recognition. They are working in a state representation mode, and their advantages include computational efficiency and flexibility. This is why we have used them as a baseline for our experimental analysis. Their modern adaptation integrate neural networks, of course, to improve decision making and handle long-range dependencies. But as stated earlier, we have also employed pre-trained large language models like Roberta and BERT, where we found out that those models return the best results with the context of F1 score that we measure. And we can see more details in the next slide regarding the results. Some very brief details regarding our experiments. We have utilized a total of nearly 56,000 of data records. We split our set in 50,000 in the training set and 5,000 in the test set. We ignored around 1,500 of data records because of inconsistencies and corrupted input. And here we list all the methods that we utilized. Most of them are from a well-known Python library, Spicy. And we have utilized transition symbol, models, as well as transformer-based models like BERT and Roberta. And the final model that that gave us the best performance of around 62% of F1 score was the pre-trained model of BERT from the PyTorch library. And this concludes my presentation. And I will give the floor now to Petros.
Okay, thank you very much, George. So hello, everyone. I'm Petros Skoufis. I'm an associate researcher at Athena Research Center, and I'll be talking about the more technical part, let's say, of constructing knowledge graphs out of unstructured data. I'm pretty sure that you got convinced from the presentation of George about the value that out of extracting information out of documents for your use cases. And I hope you got inspired and have some use cases in mind. So the process of getting from unstructured data to a knowledge graph can be split into some simple subtasks, which we will be running through together. So next slide, please. Sorry, next slide, please. Okay, perfect. Oh, no, step one, the previous one. Okay, perfect. So let's start from the case of Agroknow. Agroknow is interested in identifying food products or ingredients and hazards from texts. You can name, in your case, what are the classes of interest. So, for example, in a text like this that says that some company LLC recalls to undeclared contamination by hazelnuts, we want to annotate chocolate bars as foods and hazelnuts as hazards. And the end, the product is something like the graph on the right of the screen, where you see that chocolate bars have been annotated with the relationship type of as food products and hazelnuts with the relationship type of as hazards. The interesting thing here is that we need the step of reasoning because, as you all know, hazelnuts are also food ingredients, but in our case, they refer to hazards. So we need to think of solutions that manage to capture this semantic, the semantics existing in the text. And we will see later how we do it. Let's go in the step 2, in the second step. So after having identified these entities, we need companies like Agroknow want to have them under one taxonomy. So they have multiple classes of interests, and they want to classify all the entities in these specific classes and also identify duplicates of them. So let's add another example here. We have another company LLC that recalls chocolate chips due to the possibility of glass pieces in the packaging. So the interesting thing here is that although if they identify chocolate chips as foods and glass pieces as the type of hazard, both chocolate bars and chocolate chips are part of the same category for Agroknow, which is milk and chocolate products. So after having identified these instances, we use solutions to actually map them into an existing taxonomy and help in the organization of the knowledge in the specific taxonomy that the company is using. Let's go to the final step. So in the final step, to create a graph which actually captures all the relationships, which is the biggest, let's say, advantage of the graph, we need to extract all the relationships of interest between the instances we previously managed to identify. In the case of Agroknow, such relationships are relationships related to contamination. So as you see here, we have the relationship contaminates, which is a general relationship about contamination, but we also have some more specialized relationships like physically contaminates and allergen contaminates, which refer to the case of contamination through a physical object, such as glass pieces, or contamination through an allergen, such as hazelnuts. You see that through relationship extraction, we managed to create graphs which have common relationships. So in both cases, hazelnuts and glass pieces contaminate chocolate bars and chocolate chips respectively. But also, the systems managed to capture the fact that hazelnuts are allergens and contaminate with these specific relationships, while glass pieces are at physical contaminators and contaminate this way. So you saw just the 3 steps that we follow to construct actually the structured knowledge that we need. And next slide, please. The way we do it here in Athena Research Center is using large language models to help us solve all these steps. And don't be scared about the use of large language models. They're not here to substitute you. We actually use them with a lot of help from the experts and with a lot of integration of expert knowledge as enablers that help the experts of Agroknow solve their task. So next slide, please. So LLMs, for those who may not know, are big artificial intelligence models with capabilities to understand, summarize, generate, and predict new content. I think this definition it's not useful because everyone right now knows ChatGPT and have experimented and know their capabilities. The interesting thing here is that there are also smaller large language models out there, which are not mostly known to people that don't operate in the field, like Llama, like Mistral Nemo, who allow us to run such computations, but on a local scale and on a lower scale. And the interesting thing here is that there are a lot of ways that you can guide these models and help them adapt and solve your task. So you can imagine a large language model as an intern that you will have in your job. And the simpler way to guide them is through prompting. Prompting is a clear description of the task that the large language model have to solve. In very simple ways, you just define the task that you want them to solve. And apparently, most of the times they get it quite well. The extra step after prompting, as you see, we have an axis in the end of the screen where you see all the techniques with complexity. So after prompting, you can use augmentation using an ontology. A lot of experts have ontologies for their domains, and actually the ontology helps by explaining specifically to the model concepts that they could not capture that well or they don't know that well, and this helps them also understand better the prompt. Another way that you can do it is through examples. The same way that you're using examples when giving instructions to people, just to showcase how your instructions are actually applied. LLMs are capable of using examples, and they're actually pretty good at utilizing them to get the most out of them. And the final step, the final way that you can adapt an LLM to your specific task is fine-tuning. Fine-tuning is a bit more complicated because it allows you to intervene to the weights of the model, and it needs some expertise to do it properly, but it really allows you to actually inject a large amount of examples you have at your disposal to the model and showcase it the way of proper functioning. The truth is that there is no golden rule here, and even simple combination of these techniques, first of all, these techniques can be combined, and even with simple combinations of them, you can actually get pretty remarkable results. And next slide, please. So this happened also in our case. We used all these techniques to create large language models, open source and small ones that can run in consumer computational resources, and we managed to create two things. First of all, we managed to create a dashboard that was performing all the steps that we mentioned before, and it actually provided help to Agroknow experts to accelerate their job. So you don't have to think of LLMs as always something that will come and substitute you. They can come and enable you to accelerate your job and do it with less errors. But also even in the automated task of knowledge extraction for the food domain that we were focused throughout this project, we managed to use a small LLM like Llama 3.18 billion, fine-tuning, and actually outperform the existing state-of-the-art, which were two BERT models, InstaFood Roberta and SciFood NER, and also the baseline version of Llama. And we did it with just, I would say, simple iterations in all the techniques that we used before. Next slide, please. So summing up, I want you to have these three takeaways. First of all, like expert knowledge is essential to guide the model. So you are very lucky that I guess many of you are experts in your fields, and you can use this documented or undocumented knowledge to guide LLMs to help you with knowledge extraction. Second, we are very lucky because right now, even smaller models in domain-specific solutions manage to perform very well when they get like expert advice and expert instructions. So you don't have to think of always ChatGPT as your solution provider and not this type of resources. Even with resources scaled down, if you possess the expert knowledge needed, you can guide these models to perform very well for your tasks. And finally, LLMs are evolving at an enormous pace, and this is very interesting because this means that it gets easier every day for you to use these models, and their performance gets even better as days pass by. Like our experience the last 2 years that we're working with these technologies is that we get weekly progress, which allows more and more adoption from more people. So feel free, and I would say I urge you to jump fast into using these technologies in your fields. So thank you. That was all for our part.
Thank you very much, Petros. Thank you also to George and also to Dimitris. I would now give the floor to Bernadette and to Chanmeet to discuss the use case of Titan and the network of semantic resources for the food supply chain. Bernadette, the floor is yours.
Thank you very much. So my name is Bernadette Durand. I work for INRAE in the team of Mestia. And I'm also the coordinator for the Titan, well, one of the coordinators for the Titan project, which you will be hearing more about today. I will be presenting the network of semantic resources that we have been putting together for the food supply chain. So our aim for this presentation is to introduce Titan and to talk about the needs of the network of semantic resources and the possibilities creating this would create. I will also be presenting one of the resources we have selected and our selection criteria. I will also touch on the advantages of using resource repositories and give you a quick look at the current network of semantic resources. Next. So Titan is a Horizon Europe project that aims to increase the transparency in the food chain for the actors as well as consumers. We have 23 diverse pilots, but all of them form part of 3 focal points: food safety, sustainability, and health. So for food safety, we focus on dangerous elements and food authenticity. Sustainability is very wide. So it contains farming activities, food waste, forced labor, and deforestation-free claims, amongst others. And health mostly focuses on nutrition. Next, please. In putting together this network of semantic resources, we first had to look at what food supply chains look like in general. It's important to consider all the actors in the food chain and anticipate what data they would like or need to be available to them. We started with resources that are relevant to the Titan project, but the final goal would be to have resources for the entire food chain and eventually all supply chains. So our example today is the cacao supply chain. So cacao is produced, transformed, and stored, and eventually sold. Other actors are also possible, such as fermenters. Oh, I forget. They can go through a couple of processes. Yes, and they can also be used in other other factories, and if there are ingredients in other products. So they will also be crossing borders and moving between countries. Next slide, please. Here we have examples of the types of questions that the actors in the supply chains would be interested in answering. So we use these and many other questions to set the scope of the resources that will be required for this network of semantic resources. Some food supply chains will have very different questions, and some will be very similar to this one. It really depends on the supply chain itself. So the yellow questions, in this case, indicate sustainability considerations, and the red ones, food safety consideration. This white question over here is a connection point between different supply chains, and this is where we can create new possibilities. Next, please. So the questions that customers have can be very different from the other actors in the supply chain, and they are generally centered around these topics: the origin, the nutrition and safety, and the personal preferences and beliefs of the customers. Here we also find food safety, sustainability, and health type questions on a regular basis. I would like to emphasize that these are not the same types of questions that you would use to create knowledge graphs. For competency questions are far more specialized and tied to the exact data that is available, because you have to create the relations between the data to be able to answer the specific competency questions. Next, please. Okay, so the goal of this network of interconnected semantic resources would be that any actor in the supply chain would be able to query the available data of any other actor in theory. Of course, we would also need data sharing agreements in place to protect the information of actors and data that they need to keep private. Once this network is adopted and implemented by the actors in the food chain, it will create certain opportunities. It will increase the ease of reporting, which would be welcome in the rapidly changing landscape of food regulations. Here are a few examples. The deforestation regulation is a very hot topic at the moment, and also the focus of our use case today. Okay, there are many other regulations. Yes, thank you. There are many other regulations. These are just a few that we listed. Then it could also generate countless opportunities for circular economy. Now we come back to that white question from before: what are waste products? And cacao pulp and cacao pod husks, or in this case, would be waste products from the creation of cacao that could be used in other supply chains and for other applications. And these are not the only ones. Cacao can also be used in cosmetics, for instance. Okay, thank you. Next. This is our example of a semantic resource. In this case, we have Food On, which is a farm-to-fork ontology about food. in this diagram, you can see that the concept of a food product is linked to which part or plant of the animal it comes from, its physical state, shape, or form, what food or product type it is, transformation processes it might go through, and the container or wrapping it might be in. Next, please. Okay, and this is how we actually evaluate these resources. In this case, Foodon is relevant to all of Titan's pilots. It is currently under development and maintained by a team of people. It is adopted and used by other projects. It has excellent potential to formalize food chain concepts, as well as aligning with other resources. Its ease of adoption is high, and it has a tool to add terminology in the portals, which we'll get to shortly. And it covers the subject scope completely. That means that all the actors in the supply chains could make use of this resource. And its fair metric is 68%. Next. Yes, so semantic resource the repositories are very important in creating this network of semantic resources, because they make it easier for us in certain ways to locate resources and to simplify the process of alignment. These portals feature semantic resource hosting, searching, versioning, visualization, commenting, and recommendation. It also enables semantic annotation and resource alignments. So the relevant resource repositories for this project, for the Titan project, and for the food supply chain are, could you press next twice, please? AgroPortal and BioPortal. And there are others, next, such as W3C and OntoPortal, Obo Foundry, but the resources that we have selected so far are mostly in AgroPortal and BioPortal. Next, please. So the semantic resources can be aligned on terms with the same meaning and significance, or through user-specified relations. This diagram indicates the possible existing alignments between the resources as lexical matches. That means that they are spelled identically. And these lexical matches will be automatically detected by the resource repositories. This gives us a good starting point for connecting resources. Actors will, however, have to check that the meanings of the terms and the relations between them deliver the expected result. Otherwise, they will have to request for other terms or relations to be added to the existing resource. This can also be done through resource repositories. Next twice, please. Okay, so as we can see now, many of the resources on the graph are in the same resource repository. Some of them are in both, and so that they overlap and form connections between the different resources and repositories, which is very nice to create this network. Just as a note, BioPortal actually contains many more resources than AgroPortal. So this diagram is not indicative of its actual size. It's just the resources that have been identified for the use in Titan. Next. Okay, so now we're going to take a quick look at the actual network of semantic resources that we've created.
Yes, now I will change the PDF, Bernadette.
Yes, please.
Okay, very well. Can you see the PDF? No?
No, we can't.
Okay, let me just...
I think just go back to the presentation, otherwise we lose too much time. I can send it to whoever wants it, and I can put you on a mailing list, because this will continue to evolve for the next 2 years until Titan comes to an end.
No problem. This should be now fine. Can you see my screen?
Okay. Yes, I can. So we have the actors in the supply chain that have been sorted into different groups according to which resources they commonly use. So if you could, and then there are the transporters are everywhere in the supply chain, and regulators would be quality control and regulations, which is also present everywhere in the supply chain. And then we have general supply chain. If you could press on the green, please. So that takes you to resources that can be used by any supply chain, not just the food chain. Return to diagram, please. At the bottom, you can press on the, yes, thank you. And if you can press production at the top box, just the big one, yep, that's right. So, and you can navigate between the different sections. They're all connected. If you could press on food on, so this is the resource we had before, it will launch into the location of food on in its resource repository, which is AgroPortal. Okay, it's probably not showing that window
Indeed,
now.
because yes, because it is opening in the browser, but it did open the website. I can confirm.
Okay, so this is what it is. We can go back to the presentation, please.
Okay, I am now switching back to the presentation. Just a second.
Okay, and next.
Okay, thank you very much, Bernadette. Chanmeet, the floor is yours.
Thank you very much. Great presentation, Bernadette. And now we move on to Open Food Chain, which is all about open traceability. And Open Food Chain is very proud to be partnering with Titan Project, which Bernadette said, is an EU Horizon project. So next, please. I think we were all talking about, food, the data attributes across the supply chain. And Bernadette also touched upon a little bit about the regulations. And Open Food Chain is one of the use cases the Titan project has, which is all about traceability and actually with having a focus on EUDR. So traceability is a must-have from 2025 onwards. We know the regulations that are coming up, like CSDDD, EUDR, they're just knocking on a door. And traceability is also being demanded by consumers. They really want to know what has been the origin of this product. And also from a sustainability standpoint, especially EUDR, the regulators want to know, has the commodity been sustainably sourced from the origin that it claims to be? Are the farms been deforested while actually producing this commodity or not? So traceability is being demanded from both the sides, be it consumer or regulators, and also the supply chain across. Next, please. Open Food Chain believes in new traceability values, and I'll give you a walkthrough why we call them new and why do we believe in them. It really is about farm to fork. What we see is there are a lot of systems in the market which basically create silos. The data does not flow from all the way to the farm, either to the corporates or even the auditors. To remove those silos, what we really believe is a fully decentralized system is needed that can allow the data to flow from farm all the way to the fork. And on its way, the data is not changed, not manipulated, or not tampered with. What we also believe is in order to do so, the system needs to be accessible to the farmer as well as to the corporates and all the way again to the auditors as well. So we don't really have transaction costs. It is really easy to use, and that is what we have built so far. Open source I think we really live by the open source principle, because infrastructures like these need to be open sourced so that other valuable applications can also be built on it. So the work that we will be carrying out also for the Titan project would be open sourced so that the other participants, other companies, other valuable applications can actually be built on this infrastructure. And we believe that it should be open so that anybody can join, geography independent, role independent across the supply chain. Next, please. Like I said before, our focus really stands at EUDR compliance. And we all know that there are 7 commodities that are affected by the EUDR. And really the data, which is used for the traceability of the origin, actually is no longer a voluntary, voluntary compliance, but it is turning into more license to operate. So we need the farm level data, we need the georeferencing data, the risk assessment, the risk mitigation. Are the commodities actually complying to the local laws? All of these articles in the EUDR compliance are to be proved by traceability, that open food chain can actually provide. Let's go next. So what really is the problem? It is estimated that around 56 to 60% of the globally traded commodities cannot be actually traced back to the farm level. So if you look at the importer side, the importer gets all the information from the exporter, where the exporter actually claims, yes, the chain before me has been deforestation free. But there is no way to actually go back to the farm level and have a check. So every actor in the chain is actually relying on the information produced by the actor before. So if we really want to go to the farm level, there is no visibility. And that is why you see on this diagram, the part of the farmer, the cooperative in the cacao chain is actually gray. It cannot be traced back. Next. And I think you can press next 2 or 3 times. Yes. So what is critical here is, in order to have visibility across the supply chain, we actually connect the data from the farmer all the way up until the consumer. You can actually think of OFC as a harmonizer across the supply chain. And we provide common standards, we provide common data points so that traceability can be produced by design, and then OFC can be plugged into any system to see the traceability across all the way till the farmer. And the verifiers in between basically check whether the polygon on which cacao was actually grown is deforestation free, and all the other legislations are checked. The data is then recorded on OFC so that you can actually rely on the data. And data travels all the way from the farmer up until the consumer in an immutable way. Next, please. So we are very happy that this solution is currently being expanded to fish and olive oil under the Titan project. I think I had placed a lot of partners here. So if you, on the right, we are very happy to partner with, for example, Focus, INRAE, in our strive to expand this solution to fish and olive oil industry. If you go next, our focus today, of course, I'm explaining the cacao. So how have we been able to achieve traceability, and what is exactly the data that comes out of this traceable system? So we are working with a selection of cooperatives, in Peru and Colombia, around 21 cooperatives, processors and manufacturers, and around 5,000 farmers will actually be onboarded as we speak on this platform. Let's go next. So what does OFC really mean in practice? Practically, how does a farmer really use OFC? Every farmer that are being onboarded and trained can actually use OFC's app to trace their farm in two ways, either walk across it or trace it. So when this information gets added to the app, this information is then checked by the verifiers whether the plot was actually deforestation free or not. So the farmers actually use the app to trace their polygon / the farm. Let's go next. The EUDR checks that I said before, they follow land tenure rights, whether the production is deforestation free, or is it really the product was produced according to the relevant legislation, the risk assessment, and so on and so forth. Once the data is checked, it is then put on the OFC layer and it starts to travel across the supply chain. Next, please. So what are the data attributes that are generated across the chain? Again, I've depicted here a very simplified supply chain. Farmer is / the producer actually produces the crop, goes to a cooperative, to a processor, a trader buys it, imports or exports it, and a retailer actually transforms it either into a chocolate or actually sells it that way. What we do as part of the data dictionary / data management here is we track and trace every product all the way to its batch. So we link all the batches produced by the farmer, sold to the cooperative, then the batches that went to the processor, and then the batches that actually joined and became a container that was exported by the trader, and then all the way to the retailer. These are some of the data points that you see travel across the supply chain. And at the end, the retailer can actually look back and see which batch belonged to which product, grown where, checked, deforestation free, yes or no. A consumer can actually trace back trace a chocolate all the way to where the cacao was actually produced and be sure that this is really the origin that is claimed to be the origin. For the auditor, it is important that when a claim is done by, for example, the importer, the way to verify that claim is through the supply chain and the data attributes. The auditor also needs to know whether the claim that is being sent by the importer is true or not. So this can be used by the auditor. So these are the data attributes across the chain that are generated. And of course, when we look at the knowledge graph standpoint, it is only great that when these data attributes have a common language to be spoken, and then there are correlations that can be drawn across the supply chains, supply chains that come from, for example, in cacao's case, come all the way from Peru, Colombia, or they come all the way from Ivory Coast, Ghana, etc. So I really feel, I think the next layer could be the knowledge graphs. With that, I think that is all that is the use case about OFC. If you go next, please. For the enterprises and government authorities, like I said, this data is very, very critical to see how the EUDR claims that are being said are actually true or not. So any enterprise or government authorities or auditors can actually use this dashboard with suppliers and verified batch claims. One of the experience that we also had was this dashboard going forward can also be related to, what were the conditions out there in the farm. And again, another part is how do you incentivize the farmer? So that goes into the area of digital wallets and giving premiums to the farmers. If we go next. For the consumers, like I said, consumers can actually just scan a barcode and see the journey all the way to where the ingredient was actually produced. You don't really need to only, trust the brand, but the brands are also approaching this as a common thread that can link the consumer towards having more trust on the brand. If you go next, please. Some years of recognition, that we've had. Next, please. Just the faces around our team, and that's all I would say. That was all about OFC. Again, very happy to be part of the Titan project and helping it scale for fish and olive oil. Thank you.
Thank you very much, Chanmeet. And now we will move on to our last speaker, Theodor, who will be leading us into data pipelines. And after his presentation, we will have the Q&A, so stick around. Theodor, the floor is yours.
Thank you very much. Yeah, let's get started. So today, what I want to talk to you about are decentralized digital product passports. So I think you'll be surprised that I will not be talking really about an agri-food related topic. I am making a connection towards the end, but rather what I would really like to inspire now is for you to think about how we could collaborate based on also our developments in this part of the society and supply chain transparency. So today I want to talk to you about the societal relevance, the impact, and also the adoption methodologies that we have experienced ourselves with digital product passports. Next slide, please. So the first question that comes to your mind is, why would we need digital product passports? As you also are working towards more traceability in the food sector, also other sectors are seeing a larger demand from authorities on enhancing the visibility and traceability and accountability across supply chains. So we are looking at regulatory compliance at the level of human rights and labor standards, environmental sustainability, business ethics, consumer protection, and product information, and overall the digitalization across the entire supply chain. Next slide, please. So currently the ESPR, the Eco Design Sustainable Product Regulation, I believe. So this is currently from the European Commission, the de facto legislation on how digital product passports will look like. What do they have to, what data do they have to refer to? So about the recycled content, how much critical materials they are using. Is it water? Is it other critical materials? And we also see that we are starting to have more and more of these delegated acts that are focused on a specific industry. So for EV batteries, there's already a delegated act. For textiles, there's going to be one. For tires. So the whole world is slowly moving more towards these digital product passports. Next slide, please. So how are the digital product passports expressed? Well, I tried to make a really simple example of a supply chain with 3 tiers. 3 tiers. So the responsible economic operator that's going to publish the product on the European market, they have to present this digital product passport, but of course they have not done the full product themselves, but rather they are using an aggregation or a combination of data or data locations about their product from their supply chain partners that they have in source. So at the end, the solution needs to be interoperable at the level of all of the companies that are being part of the supply chain, even though all of them might talk different languages. In the end, the document that's being presented to the authorities needs to be coherent and present all of the facets required for compliance. Next slide, please. So currently, we are looking at a really difficult landscape when talking about interoperability, because we have two phases of the digital product passports: the upstream supply chain traceability, where you're building up your product, you need information from your collaborators. So this is more of a business-to-business setting. And here we are analyzing that data spaces are a strong contender for a good end-to-end solution with connectors, with standardized semantics for each data space, and also standardized interfaces across data spaces. For example, open API or vocabulary solutions like DayCat. So that's when you're building out the digital product passport. How about when you actually need to show it to the customers, to the legislators? You have to make it always available. It has to have a physical link to the so the digital artifact that holds all of this information needs to also be physically linked to the product. So there needs to be on the product itself a QR code, a barcode. At the moment, there's no definitive answer here, but kind of this link, and also an interface for repair events. But I'm not sure how that's ever going to be relevant for agri-food products. So let's move on to the next slide. Now, technical interoperability is only one issue. We also have the semantic interoperability. So you have all of these already existing companies that have their own ERP systems, that they are talking their own languages. They have their own data structures based on which they have been conducting their business. And of course, they're going to struggle in this adoption of standardized ways of data sharing. So that's why a really clear methodology on semantic interoperability is being proposed currently by the JTC 24 Senelec standardization working group about digital product passports. And it's mainly the main idea around this is you start with the core legislation, the ESPR, and then based on each industry delegated act, you're kind of building up your ontology through an extension. So in the diagram I have on the right, the battery ontology that stems from the Battery Act is extending the core ontology with information such as state of charge, battery health, sort of these industry specific properties. And we envision that this methodology should be resilient to adding more industries into this ecosystem of digital product passports, as an ontology can be extended based on its core description by the W3C. Next slide, please. So finally, I have tried to make a relation to agri-foods. Currently, we are looking at how we can assess our digital product passport methodology based on a agri-foods scenario that's being presented from the Plutos Horizon 2020 project. So we have taken the use case of frozen peaches and how they can be processed. So as you can see, the data flow starts from the farm in the bottom left, and then you're starting to save all of this data about the cultivation, the harvesting, and the processing, and then you're going to host it at the farmer's level, because we are thinking about a decentralized architecture. So all of the data resides with the data owner. Now, so after this step, then the peaches are taken to a processing factory where maybe some minimal information about them is shared with the processing factory so that they can conduct their business going forward. And then this processing factory, of course, they're going to add their own data, their own events that they have done about the peaches, packaging, processing, what's the factory location, what's the delivery time, and afterwards, finally, we reach to the level of the exporter. So the peaches are ready to be sold on the market. They are put in like this. I try to express a small diagram, like a box of peaches, and this box of peaches, when you would want to import it into the European Union, it would have to comply with all of these regulations about food safety, about food quality, and all of these. And this is where the exporter can start asking questions along the supply chain about what were the cultivation, for example, the cultivation practices, or the fertilization. So through this network of collaborators, of data sharing, we are really looking towards a solution to provide an extensible traceability system, so that no matter what are going to be the future of regulations on any kind of compliance of any product, we are thinking that this methodology is going to be resilient in adopting new possible legislation while also answering the existing ones, and being able to facilitate more easily the legislative hurdles around compliance checking for food products. As of right now, we are working on a I think white paper, I could call it, about this. As of right now, I cannot provide more information, as we are working ourselves with it. But if you're interested, you could drop me a message on LinkedIn or on or an email, and I'll keep in mind that as soon as we have a draft ready or a first public version, then I could share it with you, and we could start discussing about how the world of traceability in agri-foods can converge also towards the world of traceability for other products in general. And I believe this is the last slide. Could you confirm? Yes. Thank you very much for your attention.
That's right. Thank you so much, Theodor. And also thank you for making the relation to agri-food. Of course, this was very, very useful to us. And I will stop sharing the screen now so that we can actually move on to the Q&A part of the webinar. Now we do have 5 minutes more. I think that we can extend it for 10 minutes more to go over the questions. And let me just take a look. So I see, Catherine, that you have asked one question, and George has answered it.
Yes, if Catherine was not covered by the answer, of course, I'm here to elaborate more. But yeah, more or less, it's the same that I have already written in the chat.
Indeed, yeah, I see that you had a conversation, and these questions have been answered. Does anybody else maybe have a question for our speakers? You can copy the question in the chat box. Does maybe somebody from our...
I don't know, I would prefer if there are questions from the audience to get priority, but if not, maybe I could ask Chanmeet, who, by the way, the presentation was very interesting, very, very nice work. Congratulations for that.
Thank you very much.
I was wondering how the information is currently being collected. I don't know if I missed it in the presentation. Is this something that is done manually, that the actors across the food supply chain are expected to provide explicitly this information? Is there something that is done semi-automatically or automatically to some extent, or is there any room for that?
Now, thank you for your question, first of all. So as you know, our supply chain is not always fully digitized, especially on the farmer side, and as well as I would actually say also on the mid layer, the mid segment of the supply chain before it actually gets exported. So from the farmer, we collect the data through apps. They have their app, they are being trained on the app, and the data will be collected through the app. So is the cooperative as well. Then I move on to certain cooperatives that don't really have the data. They can actually send us the data if they have, digital data in their SAP system, etc. They can send us through an API. If they don't have that, they can also send us through an Excel sheet, which they usually use. So we are able to use the data of the Excel sheet, parse it, and actually use it to transform it into and record it on the chain. Then also the exporter side. So whoever does not have the data in, let's say, digitized form in bits and bytes, they can actually send us the data through existing Excel sheets, and we are able to upload the data and store it on the chain, and then ask for approval whether the data was right or not, so as to register. So that's how we develop the harmonization of the data across the supply chain. But because we know that at the end of the tunnel, it should all be through APIs, the farmers obviously will have data, through their apps, but the rest of the supply chain ultimately needs to be API harmonized. So somebody needs to act like a conveyor belt, and so are we, so we are acting that API harmonizer across the supply chain.
Thank you very much. This is what I would imagine also, because typically there is a trade-off between the effort that is required in order to collect the high quality information and vice versa. So if you strive for completeness, you need a lot of effort and high quality. Otherwise, you could also try to get as much information as possible from various sources, but compromising to some extent on quality. So yeah, if automation, if there is room for automation there, also
Yes.
techniques like what we are discussing here about knowledge graphs and LLMs could be quite relevant, I assume. And
Exactly.
I think, yeah, this relates also to a question that Hannah posted, if I was able to read correctly in the meantime. So yeah, I see from my perspective at least some room, or actually maybe a lot of room for applying these techniques to knowledge graphs, especially LLMs, to these kind of problems across the food supply chain beyond the use case of food safety that we talked about.
Absolutely, I fully agree with you, because at the end of the day, if we look back or forward in our supply chains, I definitely envision that there is a common semantic in which we communicate, and that semantic is exactly what knowledge graph can actually bring us. So what is risk, categorized as high, mid, and low risk? This is not the same language that we speak across the supply chain, and I think knowledge graphs can really take us there. Thank you.
Thank you too.
We have another question from the audience. I see that Theodor has answered it already in the chat. Dusan asked, in terms of circular economy, how could integration of data pipelines like DataPipe help industries beyond agri-food to transition towards more sustainable practices? Theodor, would you like to also expand on this while speaking, or do you think it's sufficient?
Yeah, definitely. Thank you. So currently the way that we view the impact of our research in the DataPipe project is we are trying to facilitate more visibility towards what are the actual the documentation of disassembling a product, what are the material composition of the product, so that you can foster new businesses to start thinking about, okay, how can we recycle this product? If we buy like an end-of-life EV battery, can we repurpose it for our grid? So through creating kind of this visibility of what were previously sensitive data about products, if we can find a secure way of sharing it, then there's a lot of value to be gained at the level of reusing the existing resources and being able to repurpose them for other goals, let's say.
Okay, thank you, Theodor. If there are no more questions, then I would just like to ask you all before we leave the webinar for a short picture. So this is a good time to turn on your cameras, as we would take a screenshot to memorize this occasion.
Could you just tell us if you will share the slides?
The slides from the presentation, yes, we can send it to the participants.
Great, thanks.
Okay, I think most of us are here, turned on the camera. So, okay, 3, 2, 1. Okay, I think we got it, right? Yes. Okay, very well. Once more, thank you all for attending. Big thanks to all of our speakers. And as Laurent asked, yes, we will be then sharing the presentation slides. I think that all of our speakers are okay with this. We also have a recording of the webinar, and we will be uploading it to STELAR's website for sure, but maybe Titan will do that as well. Okay, so once more, thank you all, and see you soon on another occasion. Goodbye.
Bye-bye.
Thank you very much.
Goodbye.
Thank you.
Bye.
Goodbye.
Bye-bye.
Bye.
Goodbye.